Welcome, ladies and gentlemen, to the Canberra catch-up on acids and bases, and hopefully your time in the nation's capital was a bit of a ripper one. Now, I'm just going to run through the sort of information that we did whilst you were away. Okay, one important thing is that you need to basically make sure that you do catch up and that you do get everything done. So there'll be certain things that I ask you to do. And of course you're going to need to be able to do those. Now, the first thing around acids and bases always relates to the safety. So with an acid or a base, you still need to do the same thing. So wear your safety glasses. If you get any on you, you wash it off, and that dilutes the acid, makes it less strong, so it has less of an effect. And acids really, for what we use at school, only really become a problem if you spill it into what we call the wet areas of the body, eyes, ears, actually not ears, but eyes, nose and the like, because it tends to react. So don't be like Bart, and sulfuric acid is not a toy. Okay, so let's have a look at what an acid is. So an acid is a substance which contains hydrogen ions. Okay, there's lots of different acids. There's strong acids and weak acids, but essentially they all do contain the hydrogen ions. Now, what are the common acids that we tend to use here at school? Well, these are the major ones that we use: hydrochloric acid, HCl, sulfuric acid, H2SO4, which you find in car batteries, nitric acid, HNO3, used a lot in the electronics industry, and acetic acid, CH3COOH, so vinegar, and you'll find that even in things like tomato sauce. No tomatoes, but there is acetic acid in it. Our other one is a base, and that is a substance that contains hydroxide ions. Okay, there's also a term that we tend to use which is alkali, and an alkali is simply a soluble base, so one that can dissolve into water. Okay, so there are some that don't, but most of the ones that we tend to do, and they have hydroxide ions, OH negative. Now, the common ones that we tend to use here at school: sodium hydroxide, NaOH, magnesium hydroxide, which is MgOH2 in brackets outside of 2, and that's antacid. So if you get an upset stomach, which is mainly your acid in your stomach going a bit silly, you can cool it down with a bit of magnesium hydroxide. Sodium hydroxide is what's known as caustic soda or oven cleaner, and ammonium NH4OH. But again, all have that hydroxide being present. Now, from the lesson that you were here, so this is just a recap to begin with, acids and bases contain all these things. So hydrogen ions for acids, they have a sour taste. They turn blue litmus paper red. They are good conductors of electricity. They are corrosive. And there's the classic examples down there. And for bases, they contain hydroxide ions. They have a bitter taste. They turn red litmus paper blue. They feel slippery or soapy, so hence they tend to be the cleaning agents. And then they are corrosive. Okay, so in that regard, they tend to burn, and the common ones that we use down there as well. Now, we need to measure acids and bases, and one way we do that is litmus paper that we used. But the litmus paper only tells us if it's an acid or a base. It doesn't tell us how strong that acid is, and it doesn't tell us how strong the base is. We use this scale, which is called the pH scale, which is the power of hydrogen, hence the lowercase p and the uppercase h. Now, it's a 14-point scale, so let's start in the middle. In the middle, where if you put in a substance called universal indicator, it will turn the liquid green. That is a neutral solution, so that's not an acid or a base. Okay, and water is the classic example of that. As you go from yellow to red, then that is the acid. Strong acids down here at this end, weaker acids are at this end here. So your hydrochloric acid from your stomach is around about anywhere between 2 to 3. Your weaker acids, your vinegars and stuff, tend to be up here a little bit more. Now on the other side of that is your alkalis or your bases. So again, they go from around about 7 to 14, and they'll go through from green to blue and dark blue in colour. So up here are things like your sodium hydroxides. Okay, down here are your antacids and the like. Okay, so we use this as a scale. The advantage of this scale over something like litmus paper is it tells us exactly if it's an acid or a base, but it also tells us its strength. Okay, and that's very, very important if you're going to be messing around with these sort of things. And we actually use this in industry and around our home. Now, there are 3 general reactions that we show in relation to acids, and the first one is a neutralization reaction. And with the neutralization reaction, it's actually the reaction between an acid and a base. So, and we say neutralization because those two things cancel each other out. Okay, an acid's properties and a base's properties, when they come together, they cancel each other out. So what you get when you mix an acid and a base is you actually get a salt, which is a series of chemicals, and good old plain water. Now what I need you to do is stop this video, go into the Year 9 Connect 2018 page, get into the content section and have a look at the neutralization practical. That will show you what I mean with this. Okay, so if we put red litmus, universal indicator into our acid and it goes red, we put universal indicator into our base and it turns blue, what will happen is, if it's exactly the same amount, so the hydrogen ions join with the hydroxide ions, you will end up with a green liquid, which is water. If you were to evaporate that water off, you would get left with a salt. Now we can take 2 of the more caustic acids and bases that we use. So this is oven cleaner, sodium hydroxide. We can mix it with hydrochloric acid here, and we get salt, regular table salt that we put on our fish and chips, and then we get our water occurring there. So essentially, we take 2 very harmful substances and we turn them into 1 or 2 very useful substances. So that's a neutralization reaction. The key to it is you have exactly the same amount of acid as you do base. If you have a little bit more acid, it will still be acidic. If you have a little bit more base, it will still be basic. Okay, got to be exact. Now, where do we use this? Well, we actually use this in our stomach. This is how we end up with the antacid correcting our stomach upset. Our hydrochloric acid in our stomach's all bubbling. You put some milk of magnesia in, or magnesium hydroxide, and then it reacts with the acid and it actually turns it into a salt and then into some water. In this case, because the magnesium hydroxide is not very dangerous, you can have excess of that within your system, but essentially you are neutralizing the acid in your stomach as a result. So that's a neutralization reaction. Okay, pretty common one that we tend to use. There are 2 other reactions that we tend to use. So there's our acid plus a base gives us a salt plus water on each occasion. Our next one is an acid plus a metal gives us a salt plus hydrogen gas. So that is again the general reaction. Now that happens with most metals, not all metals. Things like copper and nitric acid don't tend to react too much, but on the whole everything else tends to. And we saw that when we did the properties, because we used magnesium metal and one of the acids. Now let's run through a type example of it. So here's hydrogen chloride. We mix it with magnesium metal. Now this hydrogen here forms our hydrogen gas, so there's our H2. Obviously it's not a balanced equation at this point, and then this chloride here joins up with the magnesium and we make magnesium chloride, which goes under the formula of MgCl2. In order to balance that, so we've got the same number of atoms on either side, we simply need to put a 2 in front of the hydrogen. So we need 2 molecules of hydrogen to every 1 molecule of metal, and it produces the hydrogen gas, and then it produces magnesium chloride. This is how we make hydrogen for the hydrogen balloon explosion. We usually get magnesium, we put hydrochloric acid in, we collect the hydrogen gas, a la the Hindenburg, and then we basically set it on fire. Now again, you need to go to the Connect class, have a look at the practical for acid plus a metal as well. But we always have this general reaction that occurs. Acid plus a metal gives you a salt plus hydrogen gas. Now the last one is acid plus a carbonate. Now a carbonate is any substance that has the CO3 on the end of it. Okay, so we tend to use calcium carbonate, so CaCO3, better known as marble chips or limestone, we tend to use. Okay, so an acid plus a carbonate, and it always gives us a salt plus water plus carbon dioxide gas. Now again, having a look at how that one operates, okay, using hydrochloric acid again, so we go HCl plus CaCO3. Now, according to our general reaction, we always get a salt. Now that salt will depend upon what this one here is, so it's going to be a calcium salt. But let's start off with things that we know. We know it's got to be water, so that's H2O. We know it's carbon dioxide gas, which is CO2. And then what are we left with? Well, we can get rid of that, we can get rid of that, we can get rid of that, and you can see that we're left with calcium chloride, which is CaCl2. So what we did, and you'll have a look in the Connect class with the acid carbonate reaction, we basically mixed them together, it bubbled, and that produced the CO2. Then the calcium chloride was dissolved into the water, we evaporated the water off, and we were left with this salt here at the end, which is calcium chloride. So that's the general reaction for an acid plus a carbonate. So tick, tick. Now I'll talk to you about trends, okay? Always about trends and repeating patterns in science. So if you look at all of these, acid plus a base gives you salt plus water, acid metal gives you a salt plus hydrogen gas, acid carbonate gives you a salt plus water plus CO2. So the commonality between all the acid reactions is the salt that gets produced. Okay, and part of that salt always comes from the acid. Now it doesn't always have to be a chloride, but it has to be within that salt group, and that is the 3 acid equations, or the acid reactions. You need to know those three general rules if you can understand how you get each of them. So how from the acid plus the base you get the salt plus water. So let's have a look at that one now. Okay, so if we were to take the acid, again HCl, we mix it with NaOH. Okay, we take that hydroxide and join it with that hydrogen to make water, and then we're left with NaCl. So if you can rearrange those and work with those and understand that it's always easier to figure out your salt after you've taken away the things that you know from the general equation, then it actually comes out to be far easier. Now it's important that when you do this, that you do watch the acid reactions in the Year 9 Science 2018 Connect page, okay? Because that'll show you exactly what happens with each of them. Now, as usual, hopefully you watch this before you come back to school on Monday. On Monday, you will then need to catch me if there's any dramas, if you don't understand anything. And as always, have a nice day, ladies and gentlemen.